When a compiler looks at a fresh line of code, the Lexical Analyzer starts reading it character by character, left to right. But as it scans, it has to make a definitive choice. How does it know that age is a variable identifier, while 12 is a number? It can't rely on a built-in dictionary. Storing a hard-coded list of every single possible variable name or numeric combination is computationally impossible. Instead, the analyzer uses patterns. This animation shows how it works. Rather than checking a massive database of text, it applies a mathematical formula, a regular expression, to frame the characters. Because a regular expression describes a rule rather than a specific word, that short notation can map to an infinite set of valid strings, whether 3 digits or 3 million. This gives the compiler absolute certainty. It can recognize any valid token on the fly without needing to memorize the entire universe of possible inputs. To build these patterns, we have to master 3 atomic mathematical operators. Here's a state diagram showing our first operator, union. This acts as a logical OR. The path splits, accepting either A or B before converging. Next is concatenation, which dictates strict sequence. This linear pipeline shows we must accept A and immediately follow it with B to reach the accept state. The third, most important operator is the cleany star. The cyan arrow loops back, swallowing the letter A repeatedly for 0 or more repetitions. The 0 is crucial. A secondary path, labeled epsilon, bypasses the loop to the end state, representing a valid empty string. By combining these 3 atomic operators, we generate enough mathematical leverage to describe the syntax rules of any modern programming language. Let's assemble those operators into a practical rule for a standard identifier. It must begin with a letter, concatenated with a cleany star loop containing letters or digits. This syntax tree shows the rule. As age 99 passes, A clears the first letter node. The loop then accepts G, E, 9, and 9. With an invalid variable like 1 age, red error particles trigger instantly. Because 1 isn't a letter, the process is rejected. But parsing creates conflicts. Here, the scanner recognizes while and flags it as a keyword. But as the bracket stretches to absorb count, it builds a new, valid identifier. The compiler resolves this using the longest match principle. It acts greedily. If a longer valid match exists, it will never break the string into smaller pieces. There is a second type of conflict. What happens when a single word perfectly matches 2 completely different rules at the exact same time? Look at the keyword if. This diagram shows it matching both the generic identifier path and a specific keyword path. To resolve the tie, the exact keyword path elevates and overrides the generic one. Without these 2 failsafes, the longest match and the priority rule, the compiler would constantly misinterpret variables as keywords, breaking the logic of the source code. We can now apply these pattern rules, the greedy matching and the priority hierarchy, to a complete line of code. Salary equals 100. The scanner evaluates the text. Salary matches the identifier rule, dropping into a token box. The equal sign is boxed as an assignment operator. Finally, 100 maps to the digit rule as a number, followed by the semicolon, leaving a clean stream of tokens. This flawless, rules-based conversion of raw text into tokens is the bedrock of everything the compiler will compute moving forward. Regular expressions give us a perfect theoretical framework, but they have a core limitation. They are designed for human comprehension, not direct machine execution. This diagram shows the next phase of compiler design. We have to take our mathematical formulas and convert them into actual computational engines. The regular expression transforms into an NFA, then a DFA, before shrinking into a minimized state machine. To prepare for that step, lock down this toolkit. First, master the atomic operators. Second, remember that the compiler is greedy and favors the longest match. And third, know that exact keywords always win ties. Mastering these specification rules is the essential bridge.
It is what allows us to translate human-readable source code into the rigid computational state machines that will ultimately run it.